Welcome to EPG Pathshala. Our today's topic is optimized protocol for transport layer. Up to now, in the previous modules, we have seen the implications of mobility on the lower layer protocols like data link and network layer. We have seen that the protocols already used in wired network for data link layer, especially for the MAC layer, like CSMA CD, fails to work in wireless scenario because of the problems which are typical to the wireless scenario, like hidden and exposed terminal problem. Therefore, specialized protocols are designed, and we discussed these protocols in detail in the previous modules like MAC-A, MAC-AW, DAMA, PRMA and many more. Similarly, for the network layer, we saw that when the device moves from one network to another network, the network portion of the IP address changes and hence the connectivity to the device is lost. Therefore, we cannot rely on a static IP address for the device when it is in mobile state, hence mobile IP comes into picture. Therefore, for the network layer, mobile IP is used. So, in this way, the support for mobility is provided by using specialized protocols at the lower layers. But this is not sufficient. The support of mobility is also required at the layers higher than it, like the transport layer, especially when the devices are using internet. Now, mobile computing is a paradigm which provides services on anywhere, anytime basis. So, the mobile host also expects the same services as fixed host. Therefore, there should also be a transport layer protocol for the mobile host as for the fixed host. Now, what can be the choice of transport layer protocol from TCP or from UDP? Now, we know that mobile environment or the wireless environment itself is a hostile environment. Therefore, for that a reliable protocol is required, and for that TCP is the most appropriate choice. Now, the question is that whether I can directly use the TCP which is used in wired environment in the wireless environment. The answer is no, because TCP assumes only congestion to be the reason for packet loss in wired environment, because in wired environment where the transmission is in enclosed areas, there are specialized hardware and software. There is no other reason for the packet loss other than the congestion. So, to handle that packet loss, what TCP does is that it goes into slow start, that is it lowers the speed of transmission of packets, it decreases the window size to control the number of packets which can be transmitted. Now, this reduces the throughput. Now, what will happen when I directly use this transport layer protocol in the wireless environment? In wireless environment, there are many other reasons other than the congestion for the packet loss. For example, the signal propagation effects like a building or a tree, or during a bad weather, there can be a disconnection of the mobile device which may lead to packet loss. Then the frequent handovers, if they are not properly handled, it may lead to packet loss. And most importantly, the bit error rate of the wireless medium is very much large than the wired medium. So, in such a scenario, if I directly apply the TCP which assumes only congestion for the packet loss and goes into slow start, it will drastically reduce the throughput. Therefore, specialized protocols are also required in wireless scenario for the transport layer, so that they can support the mobility as well as they prevent the TCP to go into slow start when it is not required, hence preserving the throughput. So, in this module we will discuss the functioning of standard TCP, that is which is applied in wired network, how it behaves when there is a packet loss. Then we will see that can I directly replicate this TCP in the wireless scenario, that means we will be looking at the problems which are associated with the wired or the mobile networks, and then we will see that what will happen when I apply this TCP in this wireless network. Then we will be discussing the slow start mechanism and the fast retransmit mechanism of TCP, and we will consider a specialized protocol which has been optimized for wireless network, which is known as ITCP or Indirect TCP. We will discuss the mechanism of this protocol and the advantages and disadvantages of this protocol. Now first let us see how the standard TCP works in the wired network. Standard TCP is a connection oriented protocol. It has been tuned to work for networks composed of wired links and stationary hosts. It is a reliable protocol. Now what do you mean by reliable? The number of packets sent are regulated by increasing or decreasing the size of the window, which is known as congestion window. TCP sender uses the cumulative acknowledgements sent by the receiver. Now to adapt with the problems associated with the wired link, this window size can be changed. TCP assumes congestion to be the main reason for the packet loss. Now what is congestion and why there are no other reasons for the packet loss? In wired network, data transmission takes place using network adapters, fiber optics, copper wires and special hardware for the routers. Now this hardware typically works without introducing any transmission errors. And the software is also mature enough so it will not drop packets or flip bits. If a packet is from a sender to a receiver, it is lost in the fixed network, then it is not due to hardware or software errors. Only the probable reason can be that there is a temporary overload at some point in the transmission path, and this is known as congestion. Now what is congestion? The packet buffers of a router are filled and the router cannot forward the packets fast enough because the sum of the input rates of packets destined for one output link is higher than the capacity of the output link. So in such a situation, what a router can do is that now it cannot handle the rate at which the packets are arriving. So what it will do? It will just drop the packets. Now this dropped packet is lost for transmission and the receiver notices a gap in the packet stream. The receiver does not directly tell the sender which packet is missing, but it continues to acknowledge all the in sequence packets up to the missing one. Therefore, TCP assumes only congestion to be the reason for packet loss. Now how it handles this situation? So it follows the following step to handle the packet loss due to congestion. The first step is known as slow start, second is congestion avoidance, and the third is fast retransmit. We'll see these steps one by one. What is meant by slow start? Slow start works as follows. As we said that the number of packets sent depends on the congestion window size. To start with, the transmission starts with a congestion window size is equal to 1. So if there is an acknowledgement received for this packet, now 2 packets are sent. So one packet is sent with the congestion window size equal to 1, acknowledgement has been received, now 2 packets have been sent. Now if the acknowledgement is received for both of these packets, now 2 more packets would be sent. That means for each acknowledged packets. So 2 packets have been acknowledged, so 2 more packets would be sent. That is now the 4 packets would be sent. For each received acknowledgement, TCP increases the window size exponentially. Now, do the window size have to be increased exponentially indefinitely? The answer is no. Again, it will increase the overload. So it is increased only up to a threshold value. So from here the next step start, which is known as congestion avoidance phase. Now in congestion avoidance phase, the window size is increased linearly, that is by making an increment of 1 1 until it reaches the receiver's maximum advertised window or the packet is packet loss is observed due to a timeout or due to the receipt of duplicate acknowledgements. So what we have seen till now, that how the slow start works. Window size is set to 1. A packet is sent by this window size. So for when an acknowledgement arrives, the sender increases the congestion window by 1. So now 2 packets would be sent. After arrival of 2 corresponding acknowledgements, the sender again adds 2 to the congestion window, 1 for each of the acknowledgement. Now the congestion window equals 4. So this scheme doubles the congestion window every time, that is, the increase is exponential in nature. Every time the acknowledgements come back, which takes 1 rounded time and which is known as the exponential growth. Now the exponential growth stops at the congestion threshold. So as soon as the congestion window reaches the threshold value, further increase of the transmission rate is linear, that is, it gets incremented by 1 until the packet loss is being observed. Now how a TCP identifies that there is a packet loss? So there are 2 conditions in which a packet loss is being identified. So we will just look at these 2 conditions. TCP measures how long the acknowledgements take to return back, use it to determine which packets have reached the receiver, and provides reliability by retransmitting the lost packets. For this purpose, it maintains a running average of round trip delay and an estimate of expected deviation from the average. So if the current delay is longer than the average by more than 4 times expected deviation, it assumes packet loss and it retransmits. Now another situation in which it understands that it is a packet loss is very interesting. What is that? It assumes packet loss if duplicate acknowledgements are received. What is meant by duplicate acknowledgement? The name itself indicates that duplicate acknowledgement means you are getting the acknowledgement for the same packet again and again. So this is because the receiver acknowledges highest in order sequence number. It also, if it receives out of order packets, then also it generates acknowledgements for the same highest in order sequence number, and that results in duplicate acknowledgement. So in this case also it assumes packet loss, but due to some error on the transmission link. What happens in a fast retransmit algorithm is that only the lost packet will be retransmitted. Let us look at a small example that how duplicate acknowledgements are identified. Now suppose data segment 1 or the packet number 1 has been sent, acknowledgement received, then segment 2 is sent, acknowledgement received, segment 3 is sent, acknowledgement not received. Segment 4 is sent, acknowledgement will be sent by the receiver but not for packet number 4. Packet 4 is out of order packet. Here the receiver sends back acknowledgement for segment 3, saying that I am expecting packet number 3. It actually means that I am expecting segment number 3. Again for segment number 4, it sends acknowledgement for segment number 3. Then for packet number 6 also, it sends acknowledgement for segment number 3. Now by getting these 3 duplicate acknowledgements, so what is this? Duplicate acknowledgement for segment number 3 are sent again and again. So thus it is reasonably concluded that segment number 3 or the packet number 3 is lost, even if the retransmission timer has not arrived. So the retransmission timer has not expired, therefore only segment number 3 is retransmitted. This is what is known as fast retransmit algorithm. It assumes data segment indicated by duplicate acknowledgement is lost, and then it retransmits only that lost segment, and no time is wasted for waiting for timeout in order for retransmission. Fast retransmit is documented in RFC 2001 and RFC 2581. So up to now we have seen that TCP performs slow start and then it performs congestion avoidance, and in congestion avoidance in which it increases the window size linearly until a packet loss has been identified. So what it does in the case of packet loss? TCP reacts to any packet loss by dropping threshold value into half the current window or to whichever is larger. That is, the threshold value is dropped to half the current threshold value, or if it is less than 2, then the threshold value will be set to 2. A transmitting window size is reset to 1, activating slow start. And thirdly, the retransmission timers are reset to a backoff interval that doubles with each consecutive timeout. So these are the actions which are performed when a packet loss takes place at TCP. That is, these are the steps which actually handles packet loss, assuming that only congestion is the reason for packet loss. Now the question is that, can I apply this TCP mechanism directly to the wireless environment? The answer is no, because in wireless environment there are many other reasons for packet loss other than the congestion. We will see these reasons one by one, and we will see that how they affect the performance of any protocol in this type of network. The first problem associated with wireless links which leads to packet loss is the high bit error rate. Wireless links suffers from a very high bit error rate. It can be of the order of 10 raised to power minus 5. Now, high bit error rate causes the packets to be corrupted, resulting in loss of TCP data segments or acknowledgements. Missing acknowledgement will trigger a timeout at sender, which causes retransmission with slow start, that is with window size to be 1, and it drastically reduces the throughput. Now this situation could have been handled at data link layer itself, but at data link layer the forward error correction handles high bit error rate, but it would be wastage of wireless bandwidth when the correction is not at all necessary. Next, the temporary disconnections or the frequent disconnections also leads to the packet loss in wireless or mobile networks. When the mobile device moves from one cell to another cell, the call or service is transferred from the old base station to the new base station, a situation known as handoff. But in a particular type of handoff, which are known as hard handoff, there is a brief disconnection stage which is known as the blackout stage, when the mobile device is temporarily disconnected. That is, when the packets are transferred from old base station to new base station. So in such a time period, if any packet is being delivered, it will be lost. The temporary disconnection can also be due to call blocking, when a mobile device asks for a channel from the base station, but it does not get any channel because all the channels are occupied, and hence due to unavailability of the channels, no call or service will be provided to the mobile phone, a situation known as call blocking, and for this time period the mobile phone will be disconnected. So these lengthy disconnections cannot be handled at the data link layer, because for lengthy disconnections the forward error correction scheme would be ineffective. The disconnections can also be due to a situation where the cell sizes are small in a densely populated area. So when the cell sizes are small, to accommodate more and more users and to increase the capacity, small cell latencies result, hence the frequent disconnections, hence the mobile will be disconnected. Now the radio signals can also be blocked due to buildings or due to other objects in the environment, disconnecting the mobile phone for a particular time period. Now this disconnection period can be of few seconds, or it can also last for 1 minute. Then the power scarcity. The mobile phone can be switched off due to the power scarcity, or due to, since they are battery operated, so if the power goes down, the mobile phone will be switched off. Again, a situation when it goes into a disconnected state, and hence a packet intended for that mobile phone will be lost for that particular time period. So we have seen that there are certain situations in the mobile networks or the wireless networks, like the high bit error rate or the temporary disconnections, which may lead to packet loss. So in such a scenario, if I directly apply the standard TCP which is used in wired network, it will reduce the throughput. So specialized algorithms, specialized protocols need to be designed for wired or mobile network. Now what should be the goal of these protocols or the algorithm? The first thing is that I cannot change the entire TCP, because this is the base on which the entire internet or the WW is based. Secondly, the protocol should not go into slow start when it is not required to go. And thirdly, the mobile related problems should be isolated from the existing network protocols when fixed host and wireless stations wish to communicate. So looking at these three situations, specialized algorithm has been designed. One such algorithm we'll be discussing in this module, which is known as Indirect TCP. ITCP is based on indirect protocol model. In this approach, end-to-end TCP connection between the fixed host and the mobile host is split into two separate connections. That is a regular TCP connection between the fixed host and the intermediator, which is known as mobility supported router. It can be a base station, it can be a foreign agent in the case of mobile IP, it can be point of entry for GSM network, that is the IWF, and GGSN in the case of GPRS. Then the wireless connection between the mobile support router and the mobile host is handled by the optimized TCP, specially devised to handle the wireless devices. So using this intermediate entity, the mobile host gets a special treatment as per the problems associated with the wireless network. Now what this intermediator or the MSR does? It acts as a proxy, that is, for fixed host it appears as the wireless host, and for wireless host it appears as the fixed host. Okay, so what will happen if a fixed host want to transmit packets to the mobile host? The packets will be transmitted, they will be buffered by the MSR or the intermediator or the base station. Now here the interesting thing happens. What the intermediator will do is that it will immediately give the acknowledgements to the fixed host once the packet has been received. We will also see the implications of this thing when we will discuss the advantages and disadvantages. Now the intermediator forwards these packets to the mobile host and receives the acknowledgement from the mobile host. So if a packet is lost in transition from the fixed host to the intermediator, it will be handled as per the standard TCP functioning, that is by going into the slow start, and the packet would be resent. And if the packet is lost on the wireless link due to some transition errors, then it will be handled due to the optimized TCP, which need not go into slow start. So what has happened here is that intermediator has taken the packets from the fixed host, it has buffered those packets, sent the acknowledgement to the fixed host, and then forwards the packet to the mobile host. The foreign agent the foreign agent or the base station or the MSR acknowledges it and forwards it to the fixed host. So if a packet is lost on the wireless link, it is retransmitted with lower round trip time. Now what will happen when handover occurs? Now here the thing is important, because now let us look at the situation where the fixed host has sent the packet, the intermediator has taken the packet and it has acknowledged it. Now the situation arrives when the mobile host to which the intermediator, that is the base station or the foreign agent, is forwarding the packets, move to another network which has got a different base station, a different foreign agent. Now it registers itself to that different base station or foreign agent. But so what should be done? Now the old base station or the foreign agent has already acknowledged the packets. So these packets should be forwarded to the new base station or the new foreign agent, so that that entity can forward the packets back to the mobile host. So along with that, the socket information or the socket entities of the base station or the foreign agent should also be transferred to the new base station or the foreign agent. So ITCP does what? It says that I do not need to change the entire TCP, but at the same time it also says that the wireless links do not adapt to the standard TCP. So it says that let both the things happen. So between the fixed host and the intermediator use the standard TCP, and between the intermediator and the wireless host use the optimized TCP, and then it acts as an proxy handling the flow of packet and acknowledgement in both the directions. So during the handoff, the new base station or the new base station or the foreign agent or whatever the MSR is, takes the control of this flow of packet in both the directions, and the process continues. Nobody notices it. The fixed host do not notice that there is any change on the wireless link, and the vice versa. The problem on the wireless links are not forwarded to the fixed link, and the vice versa. This is how the protocol works. Now what are the slight changes which are made in the software of the base station and the mobile host to implement this protocol? Let us see. As proposed by the authors, the components for the software to support ITCP. At the mobile host side, ITCP can be accessed as a transport protocol by applications running on mobile host using special library calls. They are similar in interfaces and functions to the socket calls made by an application using regular or standard end-to-end TCP. But at the MSR side, that is at the base station side in the proposed protocol, most of the functionalities for supporting ITCP connection is with the MSR. So it acts as an actual bridge connecting the wired and wireless parts of the connection. It consists of a user level Unix process pumping data from one part of the connection to the other connection, and handoff support for the ITCP connection is implemented in MSR kernels. So this is how ITCP works. Now let us look at the advantages and limitations of this technique. The first advantage is there is no need to make changes in the TCP protocol used by the computers in fixed network, and that is what was required actually, or any other device which do not need optimization. Secondly, transmission errors on the wireless links do not propagate in fixed network. And thirdly, the optimized TCP is used only on the wireless link without affecting stability of internet. But this scheme has got a very serious drawback. What is it? It changes the entire meaning of TCP. TCP is said to be a reliable protocol because it maintains end-to-end semantics. Now where is the end-to-end semantics in this protocol? The entire end-to-end semantics is lost because the packets are taken by the intermediator and forwarded to the mobile host. So actually the end-to-end semantics is broken up into two parts, is split into two parts, and if in such a scenario the foreign agent or the base station or the intermediator crashes, then the whole packets will be lost, because the mobile host will never know that it has to resend the packets, because these packets have already been acknowledged by the base station or the foreign agent. Now the base station or the foreign agent removes a packet from the buffer as soon as the acknowledgement arrives. So if the mobile host now performs a handover to the new foreign agent or the base station, it takes a while before the old foreign agent can forward the buffered data to the new foreign agent or the base station. Now during this time more packets may arrive, and all these packets have to be forwarded to the new base station or the foreign agent before it can start forwarding the new packets redirected to it. So it provides high handover latency and it is very much problematic. The third and the another risky disadvantage of this scheme is that the foreign agent must be a trusted entity, because a TCP connection ends at this point. So, if the users apply end-to-end encryption, that is according to RFC 2401, the foreign agent also has to be integrated into all the security. To summarize with, in this module we have discussed the need of a specialized TCP protocol for wireless or for mobile networks. We have seen the functioning of standard or the regular TCP, that is how it handles the packet loss. We have seen that a TCP assumes only congestion to be the reason of packet loss and hence handles it by following the three mechanisms which are known as slow start, congestion avoidance, fast retransmit. That is, it decreases the speed at which the packets have been sent to handle the congestion. We have also seen that what would happen if I directly apply this standard TCP to the wireless or the mobile networks. Now, the problem would be there that since TCP understands only congestion to be the reason of packet loss, and there are many other reasons in the wireless networks for the packet loss, like the high bit error rate, like the improper handoffs, like the frequent disconnections when the mobile phone goes switched off or it enters into a region where no coverage is there. In such a situation, if the regular TCP is applied, it will drastically reduce the throughput. Therefore, there are a need of specialized TCP protocol. We also discussed a particular protocol which is known as Indirect TCP, proposed by Bakre and Balakrishna. The ITCP works in such a way that it splits the end-to-end TCP connection into two parts between the fixed host and the intermediator, which can be a base station, a foreign agent, or a IWF, that is an entry point. It can be a proxy server for the wired network and so on. So, between the fixed host and this intermediator, the standard TCP is used, and between the mobile host and this intermediator, the optimized TCP to cater the need of wireless devices are used. Okay. Now, this intermediator acts as a proxy. It takes the packets from one side and forwards it to the other side. But the problem with this scheme is that it entirely conflicts the end-to-end semantics, which is a USP of the TCP protocol. It also fails in the situations if the foreign agent or the intermediator crashes and it has already acknowledged packets to the fixed host. So, there will be no way in which those packets can be resent, because foreign agent would never understand that the packets has been lost. And also it would be a threat to security if the intermediator is not a trusted entity. So, to solve these problems, some other protocols also has been devised, which we will be discussing in next lecture. Till then, have a good day.